problems. This is joint work with Richard Kuhn, Giacomo Torlai, Victor Albert, and John Brasco. So recently, machine learning has received a lot of attention in the quantum community these days. In particular, one of the goals for applying classical ML to quantum physics and chemistry is to solve challenging quantum many-body problems using ML that could potentially yield solution better than traditional classical algorithms. However, despite the interest, many fundamental questions remain to be answered. In particular, a key question that should be addressed is how can machine learning algorithms be more useful than non-machine learning algorithms in solving these kinds of very challenging quantum many-body problems. So in this talk, I would provide some concrete answer to answering this question. So here's the outline of today's talk. First, I will provide a very brief review on classical shadow formalism, and then I would dive into discussing two tasks: training machines to predict ground state and to classify quantum phases of matter. So the main question that classical shadow formalism try to address is how can classical machines see quantum many-body system? And by that, what we actually mean is the ability to convert a quantum many-body system to a classical form that accurately captures many properties of the quantum system. In this talk, we would basically focus on classical shadow that's based on randomized Pauli measurement. So in this form of classical shadow, when you're being presented with some quantum system, what you do is you perform single qubit random Clifford rotation on each qubit, and then you perform a computational basis measurement, which allows you to gather, and that constitute one randomized Pauli measurement. So essentially, when you perform one randomized Pauli measurement, you get essentially n outcomes. And for each of the outcome, so basically each outcome corresponds to one qubit. And for each of the outcome, you can represent it using a 2x2 matrix, which we define as sigma ti. And now if you just tensor product all of these outcomes from different qubits and then average over the t randomized measurement, you get this classical shadow representation, sigma t of rho, which is an exponentially large random matrix with the property that in expectation value, this random matrix would be equal to the unknown quantum state rho that you have created. However, a nice property about it is that it only takes order nt bits to represent. And furthermore, while it's good on expectation value, there will be some statistical fluctuation. So some of the properties given would be subject to larger fluctuation, and then you wouldn't be able to preserve it or like estimate it using only sigma t of rho alone. But there are several properties that are actually preserved, including Hamiltonians, correlation functions, entanglement entropy in constant size region, as well as local observables that act on a constant number of qubits. Yeah, so now what we're going to do in the following talk, every time we wanted to represent a quantum state rho, we're just going to represent it using this classical shadow sigma t of rho, which only takes nt bits, classical bits, to store, which is very efficient, and preserve various properties. So now let me dive into the second part of the talk. So here we're going to consider provably efficient algorithms for predicting ground states. We represent some theory and some numerical experiments. So the task that we are going to consider here is that basically what the machine has to do is, given a parameter x, which is a vector of dimension m that describes some Hamiltonian h of x, the machine has to predict a classical representation of the ground state rho of x that corresponds to this Hamiltonian h of x. So you can think of this parameter x as describing certain controllable parameter that the experimentalists could control when they're preparing some physical system. For example, it could be some laser intensity that they could shine on their quantum many-body system. It could also be some description of the few-body interaction in the material that the scientists have created, or some magnetic field that they put this block of material or this chunk of physical Hamiltonian in lab. And yeah, and we're also going to assume that the mapping from the parameter x to the Hamiltonian h of x is not known exactly, which is pretty common in practice because even for a single x, if you wanted to learn h of x exactly, you have to perform some kind of Hamiltonian tomography, which could potentially be challenging. Like maybe you wanted to first prepare some thermal states of that physical system, utilize this algorithm proposed by Ewan-Tan, Robin Kothari, and Jiawen Ha to learn the h of x, but then you still didn't know the mapping from x to h of x, and then you have to try a bunch of different x and so on. So here we're just going to assume that you haven't done that kind of complicated process, and we don't know this mapping completely. And furthermore, like I said before, we're going to represent the ground state rho of x on a classical computer using its classical shadow sigma t of rho of x. So more precisely, what the machine learning model would do is it would be handed a collection of basically a set of training data, which are examples telling the machine that for this parameter xl, the corresponding classical representation of the ground state would be sigma t rho of xl. So in order to gather this training data, some complicated experimental effort has to be made. For example, given a parameter, they might have to synthesize a new material and perform some measurement on the new material to get some classical representation of the ground state. So we are just going to assume that some experimental effort has been made to construct this training data. And now what the machine learning model has to do is given a new parameter x that's not inside the training data, which would correspond to a new material that the scientists never synthesized in their physical lab. And then the machine learning model has to predict the classical representation of the ground state efficiently using the new parameter. So that's the definition of the task. And now let's look at what kind of machine learning model are we going to look at. So now given this training set, which is just a bunch of vectors mapping to this exponential size matrix, we're just going to consider a machine learning model that takes in an m-dimensional vector and outputs an exponentially large matrix, sigma head of x, that would represent sort of as a surrogate or a prediction for the sigma t rho of xl. More precisely, we're not really going to do that, but we're just going to output an efficient representation of sigma head of x. In particular, we're going to assume, or we're going to enforce that the machine learning model has to be trained within time that's polynomial in system size n and the number of parameter n. So it indeed has to output some representation of sigma head of x rather than the raw representation, which would take exponentially many bits to store. So to give a better sense of what kind of machine learning model we are dealing with and how we can efficiently train it, let's suppose that we wanted to train a neural network that's illustrated below. So it has an input layer consisting of m neurons and an output layer consisting of exponentially many neurons. So 2 to the n by 2 to the n. So basically it just outputs the exponentially large matrix. So it looks like this kind of bizarrely large model cannot be trained efficiently, but utilizing recent, so basically we showed that based on recent results in neural network theory, this training can actually be done efficiently. In particular, you can show that if you have this kind of big neural network that take in this m-dimensional vector, so represented here as sigma hat w, which takes in some m-dimensional vector and outputs this exponentially large matrix. If you train the machine learning model to minimize this cost function, so basically it's just the output of the machine learning model minus the classical shadow representation, which is also an exponentially large matrix, the Frobenius norm square, and you sum over the entire training set. If you perform a gradient descent on this cost function, you can show that after training, the neural network actually has an analytical form written in the right-hand side, where this kappa nn would be some learned function that depends on the neural network model, as well as the training set, which can also be obtained efficiently. And that kind of formalism doesn't only hold for neural networks, but a variety of machine learning models, such as kernel methods, which will be also talked about, I think, in the next talk. This kind of all of these kind of machine learning model, you can show that the global optimum after optimization have this form when you train on this training set, XL mapping to sigma t rho of XL. Particularly what it's doing is pretty easy to understand. You should think of this kappa as a learned function that tells you how you should extrapolate from the training point to a new point. that's not in the training set. So for example, if you have this x1, x2, x3, x4, what this formula is essentially doing is utilizing the exponentially large matrix associated to each of these points and just combining them through this kappa function to produce the representation for a new point x. So now, as long as this kappa function can be efficiently computed, then the machine learning model's prediction for the classical representation of the ground state for a new point x can be efficiently represented using only an order of small n times capital T times capital N. So recall that all of this sigma t of this classical shadow representation only requires an order of small n times capital T bits, classical bits to store. So this prediction would also require very few amount of bits to store efficiently on a classical computer. And furthermore, actually making predictions about using this classical representation is also easy, as we have as due to this linearity constraint. So now, after talking about the machine learning model as well as the task, the key idea, the key thing that we would like to understand is what kind of theoretical guarantee could we have utilizing this class of machine learning model. And for simplicity, we were going to focus on an ML model where this kappa is associated to an L2 Dirichlet kernel. So training such an ML model would be closely related to training, basically trying to learn in low degree Fourier approximation to this matrix function rho of x. So the rho of x is the thing you wanted to learn, and essentially doing this would be very closely related to that. And now theorem 1 shows that utilizing this ML model based on L2 Dirichlet kernel, it will capture the ground state properties accurately on average. In particular, we proved that for any smooth class of local Hamiltonians at of x in some finite spatial dimension, so we're thinking of a geometrically local Hamiltonian, such that it has a constant spectral gap, then given the number of training data n that scales polynomially in M, so the small m is the number of parameter. So small m could be large or small, it could be constant, or it could be polynomial in system size, it doesn't really matter. But the training data would have no dependence on the system size, but only a dependence on the number of parameters you have. And for each of the training point, you only need to perform one randomized Pauli measurement for each of them to construct this sigma t. So it's just like a single shot random matrix. In that case, you can show that the expected prediction error when you wanted to utilize this representation sigma hat of x to predict any sum of local observable would be upper bounded by a small constant error, epsilon. Furthermore, the training and the prediction time would both be polynomial in the number of parameter and linear in system size.
Can I ask a quick question?
Yeah.
What is constant spectral gap? What does that mean?
Oh, it's constant with respect to m and n. So the number of parameter and system size.
What is the normalization on the Hamiltonian? Like, is the norm of the Hamiltonian bounded or the norm of each?
No. The norm of the Hamiltonian could be extensive, so it would scale as linearly in system size.
Okay.
Yes. So I didn't normalize it, so it's like that.
Can I also answer a quick question?
Yes.
Does the algorithm or the amount of training data depend on the class?
The algorithm or the amount. So the algorithm is basically just this formula shown here. So it doesn't depend on the class. And the training data does depend on the class. So basically the training data would be for that class. So you have a single smooth class of local Hamiltonians, you get some training data inside of that, and then you train the ML model to perform.
But the amount of training data you need depend on some parameters of the class?
Oh, it would depend on the spectral gap. It would also depend on the locality of the Hamiltonian. So for example, if it acts on 5 versus acts on 6, 6 would be more. It would also depend on like the strengths of the local term. But here we're just going to assume that all of them are bounded, which I think is a reasonable physical assumption.
Okay. Thanks.
Okay, no problem. Yeah, intuitively, this condition is essentially saying that we are looking at a class of Hamiltonian that constitutes a quantum phase. So that's basically what this constant spectral gap could be intuitively thought of. And to establish the theorem, there are essentially two key steps. The first step is the following. It's basically utilizing the condition on having a constant spectral gap to imply some kind of a smoothness condition in the ground state space. That is, when in this entire space, the ground state would not jump abruptly. So that's why you can intuitively think of it as having constant in the quantum phase. So there's no sharp changes in the ground state. And this could be established by utilizing the spectral flow technique and Reed-Robinson bounds. So after establishing the smoothness condition in the ground state space, you can prove a generation error bound for the proposed ML model utilizing this L2 Dirichlet kernel trained on this randomized measurement data. So basically, recall that all of these sigma t are random matrices that consists of one randomized shot. So basically, you have a point XL with an associated ground state, and you do a single randomized measurement to construct this sigma t. So basically, you can show that you can prove the generation error bounds for this kind of ML model under this smoothness guarantee. So when the smoothness guarantee, when we have the smoothness guarantee from step one, we can show that the proposed ML model would have this kind of good generation error bound utilizing some standard statistical analysis plus a realization that when you consider an m-dimensional constant radius norm ball, like a sphere, the volume of that would scale exponentially in the dimension, but actually the number of lattice points would only scales polynomially if you set the radius to be constant. That's another important part because, I mean, that fact would imply sort of the BC dimension of the object that we're dealing with. And the BC dimension will be bounded because the number of lattice points in a m-dimensional sphere is polynomial for a constant error. And then we can utilize that to prove the generation error bound. So now one key limitation of theorem one is that I've explicitly said this epsilon can only be a constant. And the reason is because, so if you fix epsilon to be constant, then the number of training data actually only scales polynomially in M. But if you also consider epsilon to be like super small, then it would actually scale exponentially in M. And note that we're considering a classical machine learning algorithm here. So it's all classical. When I say the time, it's all classical computation time. There's no quantum computation. So one might wonder, what if you train a quantum machine learning model? What if you train like a quantum learning algorithm? Could it overcome this kind of exponential scaling in the prediction error? So in one of our appendix, we proved that actually any quantum, as well as of course classical, because classical are quantum, any quantum machine learning algorithm will require a number of training data that scales similarly to the scaling of this algorithm, this classical ML algorithm that we consider here. So essentially, and the key idea is similar, is that the key idea is that the number of lattice points in an m-dimensional sphere indeed scales something like m to the power of 1 over epsilon. So there's just no better way because the BC dimension is just that large. So even a quantum machine learning algorithm would not be able to overcome it due to known results in quantum learning theory. So yeah, so basically what it says is that the advantage of a quantum machine learning model can only be polynomial and can never be like exponential. So now, after talking about how a classical machine learning model could be used to predict ground state and have some rigorous guarantee, now we wanted to understand if a non-machine learning algorithm could also be used to do the same task. In particular, in proposition 1, which is just a combination of very standard results in complexity theory, one could easily show that if there is a classical polynomial time randomized algorithm that could achieve like this average prediction error of 1/4 for any one local observable O and for any smooth class of local Hamiltonians, in 2 spatial dimensions. So note that previously it works for any spatial dimension, for example, 3. Here we only consider 2. And also with the constraint that we have a constant spectral gap, then you can show that NP-complete problems can be solved in randomized polynomial time, which is highly unlikely. And if you assume that RP is not equal to NP, proposition 1 tells us that a non-machine learning algorithm cannot achieve the same guarantee as the machine learning algorithm. So going back to our original question, can machine learning algorithm be more useful than non-machine learning algorithm, and why is that? The combination of theorem 1 and proposition 1 tells us that yes, essentially.
Sorry, Robert.
Yeah, your question?
Can you say what's the non-machine learning algorithm versus the machine learning algorithm? I'm not sure.
Oh, sorry, I couldn't hear clearly.
Sorry, could you say what's a non-machine learning algorithm versus a machine learning algorithm?
Yeah, so basically, how I define it is that in the machine learning algorithm, you're allowed to be given this training set. So you have a training data that you can utilize to perform computation. But in a non-machine learning algorithm case, we're assuming that it couldn't learn from data. So it's just like a fixed algorithm. And that's sort of how we define it. And basically, the key idea is just that in the machine learning algorithm case, all it has to do is to take the data and generalize from the data to perform computation. And that could be much easier, like significantly easier than computing everything from scratch. So basically, the training point already solves the hard bit of the problem. And all the machine learning algorithms doing is just generalizing from the hard bit to other new instances. The classical, but if you don't have that data, then the problem suddenly becomes very hard. And that's why you have proposition 1 and theorem 1. So they didn't really contradict with one another in any way. It's just the fact that if you can learn from data, that's just more powerful. So for example, if you can gather some data from nature, which operates quantum mechanically, so you can think of the nature as being a quantum computer. And if you could gather some data by performing physical experiments, that data would also contain some BQP power and may not be efficiently generated using a classical computer. So in those kind of cases, you can have a classical machine learning algorithm that could outperform a classical algorithm that do not utilize data. So it's not like a neural network is powerful or anything. It's just the availability of data help the computation significantly.
Sorry, I missed one other thing. Could you say that, Robert? What was the distribution on the examples that you're?
Yeah, so the examples are sampled uniformly at random. And we are also considering that the prediction error is the same uniform distribution over the entire space. That's quite important. I think similar results were also seen in some kind of like some learning of DNF or something like that, or some learning of some function. I think Ryan O'Donnell are probably more familiar. I think there are certain classes of problems where it's easy with uniform distribution, but actually hard if you consider arbitrary distribution. And this is actually one of them. So it's only easy. That is, you can achieve this theorem only under uniform distribution. If you consider some weird distribution that are localized at certain points and so on, then it could potentially become much harder. So now I'll just briefly go through some numerical experiments since using up a little bit of time. So
can I ask another question about the previous thing?
Yes.
So the training data is of polynomial size, right?
Yes, it's of polynomial size. Okay,
so this classical algorithm with polynomial size data is solving an NP-hard problem, or
no, it's not really. Because it's for any smooth class that have a training data. I think that's also maybe what Ryan O'Donnell was asking. It's not like with just one set of training data and then now you can solve all Hamiltonian. It can only solve a smooth class within that smooth class of Hamiltonian. So basically, if you have same system size, but maybe there could be multiple different smooth class, then you would need training data for different smooth class. So maybe like different quantum phase. So you have one quantum phase, another quantum phase. You get data for this quantum phase. And then the machine learning model could predict within this quantum phase But if you have a different quantum phase, then you need data for that as well. So, and there's potentially a large number of different smooth class of local Hamiltonians for a fixed system size. And yeah, so yeah. So,
and does the problem remain hard if you fix the smooth class?
I mean, but if you fix the smooth class, then that's also if you fix your system size. So then it's not, I mean, there's no dependence on n going. So yeah, so I'm not sure how, but yeah.
Maybe it means if there's like one smooth class for each value of n.
Oh, but then you can always pick it in some weird way. Like if you, like if you define it such that you have one smooth class for each value of n, you can always pick the smooth class such that this function becomes undecidable, and then it just becomes hard. Like you can pick it in some way. So you maybe if you pick it in a polynomial way, you can pick the smooth class for each value of n, and that could be selected using a polynomial time classical algorithm. Then that is a situation I'm not entirely sure what is the complexity of that. So like if you only pick one of them. So yeah, so I think that's a reasonable one to consider. But in that case, I'm not entirely sure if that's still hard, or it could still be hard. At least that's what I felt. But it might be easy.
So it could be the case that if instead of given data, if the classical algorithm was just somehow told what the smooth class is, I don't know how this would be done, but like, so say the smooth classes had a name or something, and was given this information, then the classical algorithm might be able to solve this in polynomial time without training data.
So that I'm not sure. So that I'm actually not sure. Because I think it depends on whether there are sparse languages in, I mean, I think it depends on whether there are sparse languages that's not in BPP, but in MP, which I tried to check that, but I think there's no answer for that one yet. So there could be hard problems, but yeah, it depends on this, like this study about sparse languages in order to properly answer that question. But I've also thought about it, but I haven't found a clear, unambiguous answer to that yet. So that's a good question.
Thanks.
Yeah, so now here I'll just quickly show some of the numerical experiments that we consider. So here we consider a one-dimensional Rydberg atom array, and then we train a machine learning model on a training set of only 20 points to predict the ground state for other points. So it's also, this one is also simpler. So the parameter space is only 2-dimensional, and then we have all these randomly sampled training data shown as a gray circle, and now we're just trying to train an ML model such that it could predict the ground state for the entire space. Particularly, we test them on these 3 points shown here. And then here are the prediction. The black markers are the prediction from the ML model, and the solid lines are the exact values computed by performing a time-consuming DMRG, and you can show that it matches up pretty well. On the other hand, if you consider a very naive strategy where for each of the testing point, you just pick the closest point in a training set and then just say, oh, the ground state is that, you can see that it performs much worse than training a proper machine learning model. Similar situation also holds when we consider predicting ground state for a 2-dimensional system. So this is a 2-dimensional random Heisenberg model where the ground state is pretty challenging to solve. So we're doing some kind of a snake-shaped DMRG, which would scale exponentially in the width. So yeah, and then here are the prediction. This is the prediction from ML model. It's a prediction of 2-point correlation function from ML model, and this is the exact values from DMRG. And visually, it's pretty similar. There are indeed some small amount of error, prediction error inside of it, but visually you can see that it's pretty close in practice. And we're actually only using n equal to 100 number of training set. So in practice, it actually performs much better than our theoretical guarantee, because actually in the theorem, when I say n is polynomial in M for a fixed epsilon, so let's say you fix epsilon to be 0.1, when I say this polynomial, it's actually m to the power of maybe a few thousand or a few millions. So it's not really efficient from a practical perspective, but when you actually run it, it's much better than our theoretical guarantee has. So now, after talking about the second part on predicting ground state, I'll just quickly storm through the part on classifying quantum phases of matter. So here, the task is much more well-studied. Basically, given a quantum state, you wanted to predict which quantum phases of matter the state is in. And we will again represent the quantum state using this classical shadow representation. So here, similarly, we're going to consider a training set telling you that, oh, for this classical representation of the quantum state, this is the associated phase. And for that classical representation of the quantum state, that is the associated phase, and so on. And now, after training on this training set, the machine learning model has to predict for a new state, what is this phase? Is it a trivial phase, symmetry broken phase, topological order phase, and so on. Essentially, what the ML model would do is it would try to find, basically what the ML model should do is it would try to find some classifying function that could well separate the phase of matter. So for example, if you consider symmetry broken phase, there's typically a local observed O that can be used to classify between the two phases. In that case, the classical ML model only needs to learn a linear function, which is very easy by training a linear classifier. However, if you just utilize this simple ML model to try to classify more exotic phases, such as the topological phase, then proposition 2, proven in our paper, shows that it's impossible. So basically, if you have two distinct topological phases, there's no global, there's no local as well as global observable that exists that could be used to classify between the two. So this is a basic consequence of the definition of the topological phase. But this proposition is kind of interesting on itself. So now, basically what it says is that we need a much more powerful ML model that could learn nonlinear function. For example, some quadratic function or a more generic, a more general analytic function. In order to do so, we're going to utilize the standard technique in kernel methods. We're just going to learn a linear function in an infinite dimensional space where we map each state rho to an infinite dimensional vector given here that includes all the R-body reduced density matrices as well as higher degree expansion of these reduced density matrices. So we'll call this the feature vector phi shadow. So training so basically what we're going to do is we're going to learn a linear function in this expanded infinite dimensional feature space, which will be equivalent to learning a nonlinear function in the original quantum state rho. And all we need to do, basically in order to efficiently train that, is to be able to compute the inner product. And the inner product could actually be evaluated efficiently through some algebraic manipulation. You can see that the inner product could be given by this doubly exponential formula. And computing this thing, which we refer to as shadow kernel, only takes time linear in system size and quadratic in the number of randomized measurements we perform, t squared. So actually training such a classical ML model could be extremely efficient in practice. And we also give a rigorous guarantee for it. We show that if there exists a nonlinear function of few body reduced density matrix that could be used to classify the phases, then this classical algorithm that we discussed, basically learning a linear function in this infinite dimensional space, could learn to classify these phases accurately. And the amount of training time, training data and computational time would both scales polynomially in system size. Furthermore, this ML model would construct this classifying function efficiently, explicitly, such that it could help physicists to better understand the phase structure. And in various cases, which I listed here, there does exist a classifying functions that acts only on few body reduced density matrices if you assume a constant spectral gap for the state that you're looking at. That is, it's associated Hamiltonian has a constant spectral gap. And what the theorem 2 is saying is that as long as this classifying function exists, then the machine learning model utilizing this shadow kernel is guaranteed to find it. Similar situation, it also works pretty well in practice, which we show here. So here we consider a one-dimensional symmetry-protected topological phase. So this is a one-dimensional spin chain called the bound alternating XXE model, which exhibits 3 different phases. And what we're going to do is slightly different from what we proved, because I mean, we already proved that it would work. So now we're going to consider a harder task for the numerical experiment. We're going to consider doing it unsupervisedly. So you don't have a label training data. You're only given a bunch of states. And now the machine learning model has to figure out what are the states and how the states form into phases. And essentially how we do that is still utilizing this feature map, this shadow feature map that we defined that maps a quantum state. So basically what it does is it maps a quantum state into a classical shadow and then utilize that classical shadow to define this infinite dimensional feature vector into an infinite dimensional space. And what this unsupervised ML model is doing is it's looking at the infinite dimensional vector space, a Hilbert space, and then just finding a low dimensional subspace that have the largest separation of the data points. And here in C and D are the two-dimensional subspace that the unsupervised machine learning model finds. And you can see that for C, we consider delta equal to 0.5, which only consists of two phases here. So you can see that it figures out that there's two phases. And for delta equal to 3.0, there's three phases. And the machine learning model figures out the three phases. And similar situation also holds for a two-dimensional topologically ordered phase. You can train this unsupervised machine learning model to classify between a topological phase consisting of states where we start from the torical ground state and apply a constant depth random circuit on top of it, and a trivial phase which consists of product state and applying a constant depth random circuit on top of it. So here in figure C, we show the classification accuracy. That is, we use the unsupervised machine learning model to cluster it and then check how it works. And the green line is essentially the performance of the unsupervised machine learning model. So when the depth you applied is low, like it's constant depth, then the performance is pretty well. But when you increase the depth, then the two phases will become more and more indistinguishable. And then in that case, the two phases would just be collapsed. And that's also what the machine learning model figures out on its own. We also compare it with convolution neural network, which is a model that people have considered before, and which would you can prove that it would be equivalent to trying to learn an observable for classifying topological phases. And since we already proved that there's no observable that could be used to classify phases, this purple line, just a convolution neural network, is deemed to fail. And you can see that after just applying a single random circuit depth, it just drops to 0.5 accuracy, which is equivalent to just performing random guessing. So now to conclude, we proved that classical ML models informed by data from physical experiments could effectively address some quantum many-body problems. In particular, as a consequence of Theorem 1 and Proposition 1, we rigorously established the advantage of classical ML models over classical non-ML algorithms. So more generally, just classical algorithms that doesn't have access to data. I think that should be more precise. And some of the interesting open questions include, what are some advantage of ML over non-ML algorithms? That is, whether learning from data would be helpful in other kinds of tasks, potentially other quantum tasks, or maybe some classical tasks, not sure. Can we also establish advantage in other tasks? And the second question is, can we also prove rigorous guarantee for other kinds of quantum problems utilizing classical machine learning algorithms? And finally, another twist on what I was talking about, you can think of it as providing a very strong baseline for quantum machine learning algorithms. Essentially, people have been thinking about using quantum machine learning algorithms to like predicting ground states or maybe classifying phases, more on classifying phases. Essentially, what this work says is that for those kind of tasks, it's kind of already very easy for classical machine learning algorithms to. So the advantage you would get from using proper quantum machine learning algorithm would also be limited, despite them being a very quantum mechanical problem. So could we actually find a useful class of quantum learning problems with exponential quantum advantage? It's still a big, it's a very important open question to further address. And actually, me and Jordan and Sitan Chen and Jerry Lee have made some progress for the last question, where Jordan would actually provide a presentation in the talk after the next. So that's it for my talk. Thank you so much for listening.
Thanks for your talk, Robert. We have a couple minutes for questions, so does anyone have any questions?
I have a question about the classical shadow with the random poly.
Yes, you mean the first few slides?
Yeah. So I guess I would expect the expected amendment outcomes already to the exponential close to 0.
Sorry, I think I couldn't hear properly.
I mean, so the shadow is a tuple of outcomes where each of them is a product of random product of polys, right? And
Yeah.
I would expect such the outcome of such the expected outcome of such a product to be close to 0, exponential close to 0.
Oh, you mean the expectation value of this?
One of the products is sigma.
Sorry. I think maybe my internet is not good. Couldn't hear very clearly. So one thing to emphasize is that the sigma are actually not product state. They're actually not positive semi-definite. And actually, this whole representation is not positive semi-definite. That's why I always refer it to just a matrix. It's not a quantum state because all of these sigma actually have negative eigenvalues, and that's why you get this. If all of these are just like, for example, if rho is a pure state, and then all of these are just like product states, I mean, are just like also quantum state, then the tensor product of them is a quantum state. And when you average over them, that would be mixed. So then this equation would not hold. So actually the reason that this equation holds is indeed because all of these sigma are have negative eigenvalues. They actually have some positive and negative. Does that, yeah, I still couldn't hear, but I hope, is that the confusion or is that the question?
Yeah, so I guess my question was when you randomize the individual poly measurements, each of them is bounded by 1, and each of them is random. So like if you're measuring say a product state and you have all these independent
Yes.
how do you get a very small boundary?
Oh, they would actually not be independent because for this sigma 1 to sigma n, they're performed by doing a parallel measurement. So there will be correlation between different sigmas. So that's how you capture some entanglement properties using this formalism. Hello? Sorry.
Okay, so let's make progress again.
Okay.
Now we're moving on to Lucia. You're getting talked about.